Now we're going to move into 3 dimensions. So far in our calculus experience, we've mainly stuck to 1 or 2 dimensions. But life is in 3 dimensions at least. So let's look at this. This fancy R with a 1 denotes one real number axis, R1. So this is R1, 1 dimension. If you want to plot things in R1, you would draw a number line. So here's the number 0, here's the number 1, here's the number 2 on the number line, here's -1. This is one real axis. So points on the real line look like just a value, x. So points in R1 look like just numbers, x1 or x2. That's one real dimension. We've also been playing with things in R2. That's when I have 2 real axes instead of just one, an x-axis and a y-axis. So in R2, we're pretty much comfortable with drawing 2 coordinate axes. We get an x-axis, a y-axis. Points in R2 have an x-coordinate and a y-coordinate, so there's x comma y. 2 different points could be x1, y1, or x2, y2. So those are points in R2. But new maybe for calculus is R3. R3 has 3 real axes. It's usually depicted this way. So I have an axis pointing straight up, an axis pointing to the right, and I have an axis that's poking you straight in the eye. This axis is coming straight up right out of the paper, but we draw it in perspective because our paper is in 2 dimensions. The way that we're going to label these axes in our course is by having this axis coming straight out being the x-axis, the axis to the right, y, and the axis going up, the z-axis. Other people might label these differently, but for us, we're going to label them x, y, and z in this way. Now, of course, the x-axis also goes down back into the page. Y goes left and right, and z goes up and down, but I usually avoid drawing those because it makes the picture look a little bit more messy. So what does a point look like in R3? To get a point in R3, you travel some distance along the x-axis, then you turn a 90-degree angle, go some distance in the y-axis, and then you go straight up and travel some distance in the z-axis. That'll land you at a point x, y, z. So points in R3 are lists of 3 real numbers. They look like x1, y1, z1, or x2, y2, z2. These are different points in R3. So the point 1, 1, 1 would be 1 unit in the x direction, 1 unit in the y direction, and 1 unit in the z direction. So we have points in R3. We can also calculate distances in R3. So if I have 2 different points in R1, the distance between them is the absolute value, x1 minus x2 in absolute value. If you'd like, you can write the absolute value as the square root of x1 minus x2 squared. Now, if you're in R2, 2 dimensions, we could calculate distance using the distance formula. That's x1 minus x2 squared plus y1 minus y2 squared. And then if I'm in R3, I could just write down what you might expect for distance. Distance in R3 is given by x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. We could also find midpoints. The point right in between x1 and x2. The point in between x1 and x2 is the average. x1 plus x2 over 2. The point in between two different points in R2 is similar. It's x1 plus x2 over 2, y1 plus y2 over 2. So you average the coordinates to get a point right in the middle. And lastly, in R3, I have a similar statement. The midpoint is found by averaging the coordinates together. So there's R1, R2, and R3. And there's actually R4, R5, R6, and Rn. You can have n be any integer you'd like, and there's an analogous Rn for that situation. In our class, though, primarily we're going to be dealing with R3. So I'm going to ask you a question to think about. What are these equations telling me if I'm in R3? Now, this is going to be a little bit different than you expect, maybe. So I'm going to write down a few equations, A, B, C, and D. Let's do 4 of them. The first equation will be x squared plus y squared plus z squared equals 1. The next will be x squared plus y squared equals 1. Then let's try x squared equals 1. And then lastly, let's do the equation z equals x squared. Okay, so what do these equations give me if I'm in R3? What points satisfy each one of these? Well, for A, you could write this expression, taking the square root on both sides, as the square root of x minus 0 squared plus y minus 0 squared plus z minus 0 squared equaling 1. Now, this tells me that the points that satisfy equation A are the points that have a distance away from 0, 0, 0 equaling 1. What I did here is I wrote equation A using the distance formula. So the distance away from 0, 0, 0 should be 1. If you think about 3 dimensions, what points are always a distance 1 away from 0, 0, 0? Well, that's a sphere. It's a sphere of radius 1 centered at the origin. That's different than B. Now, if you're comfortable with R2, equation B in R2 would be a circle of radius 1. But I'm not in R2, I'm in R3. There's no z appearing explicitly in equation B. I don't see a z, meaning any value of z whatsoever is acceptable as long as x squared plus y squared equals 1. The only thing that affects equation B are the x and the y coordinates. So if I'm at any height z, remember z is the axis going straight up. If I'm at any height at all, I get the equation of a circle. So imagine a circle being at every possible height z. You get a cylinder. You get a cylinder. So let me try to draw a cylinder. So the z-axis is coming up, and then in the cylinder, I have the x-axis over here and the y-axis over here. In the xy plane, I get a circle of radius 1, and that's going to be the same circle at any height z. So this cylinder actually goes up and down forever, but I just drew part of it. That's equation B. Now, equation C, remember, I'm in R3. Equation C, if I were in R1, equation C would be true if x was plus or minus 1. but I'm in R3. So x can be plus or minus 1, and then after that, y and z could be anything. So you actually get two parallel planes. You get two parallel planes. Let me try to draw the picture here. So I'm in R3, so I got three axes. One coming straight out, that's x. One going to the side, that's y. One going straight up, that's z. So here is x equals plus 1, and then back here would be minus 1. The x values have to be plus 1 or minus 1, but the z and the y values could be anything. So I actually get a plane centered at plus 1 and another parallel plane centered at minus 1. That picture's not so great, but I get two infinite parallel planes. They go left and up forever. You know, two parallel planes, one at 1 and one at negative 1. Okay, let's do our last equation over here, equation D. So let's draw our coordinate plane again, our three-dimensional axis system. So here's x, y, and z. So z is equal to x squared. So if I'm only looking at the plane, the xz plane, I get a parabola. So let me try to draw a parabola in the xz plane. So it might go like this in perspective. Might go like this. So there's a parabola in the xz plane. But then y could be anything. At any value of y, I get the same picture. So you can imagine sliding this parabola to the left or to the right. So I'm going to try to depict that here. So you get like a parabola. I guess it's the ultimate like half pipe or something, because this goes up forever and to the left and right forever, getting like the most extreme half pipe ever, I guess. There, I'm shading in to give it perspective, but that would be a description of equation D. All right, great.